All right, welcome. Today, we're going to dive into the science that literally shapes the world around us. I'm talking about everything from the fence in your backyard to those massive tunnels that get bored straight through mountains. We're talking about surveying. So let's just jump right in with a huge question. How in the world do you build a perfectly straight bridge or tunnel on a planet that's, well, a giant spinning ball? We love our straight lines, but we live on a curve. It feels like a paradox, doesn't it? Well, solving that exact problem is why surveying exists. And boom, there's your answer. At its heart, surveying is the science of figuring out exactly where everything is. It's all about nailing down the precise horizontal, vertical, and even the angular relationships between different points. Then, you take all that messy, real-world 3D data and you translate it onto a nice, neat, flat map or plan.
Now, to even begin to do that, a surveyor has to make a really big decision right at the start. Are they going to pretend the Earth is flat for a bit, or are they going to deal with its real curved shape from the get-go? And that choice, it basically splits the whole field of surveying right down the middle.
So, on one side, you've got what's called plane surveying. This is what you use for smaller projects. Think anything under 250 square kilometers. You can just assume the ground is flat. All your lines are straight. Every triangle adds up to a perfect 180 degrees. It's nice and simple. But for the big stuff, mapping whole countries or continents, you have to use geodetic surveying. This is where you account for the fact that the Earth is a sphere. And here, the shortest distance between 2 points isn't a straight line. It's actually an arc. And this right here is a perfect way to picture the difference. If you're just mapping out a local park, a simple, flat plane triangle does the job perfectly. But if you're trying to map, say, North America, you have to use a spherical triangle. Those straight lines actually bulge outwards, following the curve of the Earth. And get this, the angles inside that triangle will add up to more than 180 degrees. Kind of wild, right? Okay, but here's the part that really shows you the kind of precision we're talking about. Over a distance of 12 kilometers, that's about 7.5 miles, the curved arc on the surface of the Earth is only 1 centimeter longer than a perfectly straight line drawn between those 2 points. 1 centimeter. It's a tiny, tiny difference, but if you ignore it, those single centimeters start to add up and can lead to massive errors down the line. So, quick pop quiz. Based on what we just heard, how much longer is that 12-kilometer arc compared to the straight line cutting through the Earth underneath it? If you were listening, you got it. It's just 1 centimeter. It's a fantastic reminder of the incredible, hair-splitting precision that surveyors have to work with every single day. All right, so you figured out if you're working on a flat plane or a round planet. Awesome. Now, how do you actually get that massive piece of land onto a tiny piece of paper? This brings us to the surveyor's toolkit, and it all starts with the concept of scale. So, the mathematical core of any map is something called its representative fraction, or RF for short. It's just a simple ratio, a distance on the map compared to the corresponding distance on the ground. So if you see an RF of 1 to 1,000, that just means 1 centimeter on your map represents 1,000 centimeters, or, 10 meters out in the real world. Now here's a question that trips people up all the time. Which of these is the larger scale? Is it A, 1 to 500, or B, 1 to 50,000? The answer is A. It seems backward, but just think of the representative fraction as an actual fraction. 1 divided by 500 is a much bigger number than 1 divided by 50,000. So, a large-scale map actually shows a smaller area, but in much, much greater detail. Okay, but let's throw a little wrench in the works. Let's say you've drawn this perfectly accurate map. It's got a precise numerical scale on it, like 1 to 1,000, but it's on paper. And over the years, that paper might shrink or warp because of humidity or temperature. All of a sudden, your super precise numerical scale is just wrong. So what do you do? And here is the absolutely brilliant low-tech solution. Surveyors put a graphical scale bar right on the map itself. Why? Because if that map paper shrinks by, say, 2%, that little scale bar shrinks by the exact same 2%. The relationship, the proportion between the map and its scale, stays perfectly locked in no matter what happens to the paper. It's just a genius bit of problem solving. And you gotta remember, surveying isn't just one thing. It's a whole family of different fields. You've got topographical surveys for mapping out all the hills, valleys, and rivers. Cadastral surveys for defining those all-important legal property lines, where your yard ends. Then there's engineering, hydrographic for mapping underwater, even archaeological surveys for mapping ancient sites. And they all depend on these same core ideas. So, no matter what it is you're mapping, there are some, let's call them unbreakable rules that make sure your work is actually accurate.
So let's get into the first and honestly, the most important principle of all. This right here is the golden rule. You must always, always work from the whole to the part. What that means is you have to establish your main big picture control points first with the absolute highest level of accuracy you can manage before you even think about filling in the smaller details inside.
And to really get why this is so critical, let's look at what happens when you do it the wrong way. If you start by measuring from one small point to the next, any tiny little error you make in that first measurement gets carried over and added to the second one. Then that combined error gets added to the third, and so on and so on. By the time you reach the other side, all those tiny little mistakes have snowballed into one giant, unacceptable error. But if you do it the right way, from the whole to the part, you stop that from ever happening. You start by locking in your main boundary points with maximum precision. Now, when you go to fill in the details inside, any small error you make is trapped in that one little section. It can't escape and contaminate the rest of the survey. You're basically localizing your errors instead of letting them run wild. All right, on to the second big rule. You just can't define a new point in space with only one measurement. It's impossible. To fix a new point, let's call it point C, you absolutely have to measure to it from at least two other points that you already know the location of, A and B. That creates a triangle, and it locks that new point C into one single, unchangeable position. Okay, pop quiz number 2. Let's see if this is sinking in. What is the absolute minimum number of known existing control points that you need to accurately pin down the location of one new station? The answer, of course, is 2. 1 point just isn't enough to fix a position. You need 2. So we've talked about distance and where things are, but that's really only half the battle, right? To make a map that's actually useful, you need direction. You need to know which way is north. But as it turns out, north isn't nearly as simple as you might think. Okay, get ready for a mind bender. Your compass, it doesn't actually point to the North Pole. Not the geographic top of the planet that we call true north anyway. It actually points to something called the magnetic North Pole, which is a point up in the Canadian Arctic where the Earth's magnetic field lines plunge straight down into the planet. And these are two totally different locations. And that angle, the difference between where your compass thinks north is and where true north really is, that has a name. It's called magnetic declination. This number is absolutely essential because it lets a surveyor take a reading from their magnetic compass, apply that correction, and figure out the true geographic direction. And to make it even more complicated, that angle is different everywhere you go on Earth. And that leaves us with this one big, kind of tricky question. A surveyor's whole job is to create a permanent, accurate, unchanging record of the world. But what happens? What does that even mean for accuracy when one of your most fundamental reference points for finding direction, the magnetic North Pole itself, isn't fixed at all, but is actually wandering across the face of the planet year after year? It's a fundamental challenge right at the very heart of how we measure our world.